Actually, thank you so much. It's such an honor to be here. I've been watching these WoodSolutions for several years now, so it's great to contribute and hopefully tell a great story. So, yeah, today I'm here to discuss the St. Luke's Health case study. So this is a project which is just being finished in Tasmania, in Launceston. For us, we worked on this project with Terroir Architects, who are an amazing team out of Hobart, who won the competition as part of a tender put out for St. Luke's Health themselves directly. And this is a bit of the story and how we went about designing the building. So for us, I'll start with a project overview. So because St. Luke's Health is a local Tasmanian-owned basically health business, they had two mandates for the project. They wanted it to be a Tasmanian project, Tasmanian jobs, as much potentially Tasmanian timber as possible, and a healthy project. They wanted to set a precedence for just not only just carbon reduction, but also using as many biophilic products as possible and really creating a building of the future with health in mind. This is the existing structure. So at the time of the competition, Terroir and the team came into the building. In the bottom left picture, you see there where they have the painted brick. It is a very popular cafe. And the right-hand side, which you see in the rest of the pictures, was basically an open garage, which was used for many years repairing cars and automobiles. This had some amazing features in it, with some very old and heritage hardwood timber columns and trusses. So an amazing brick facade, which was, while not, the building didn't have any formal heritage requirements, it certainly had a very impactful nature on the ground floor plane. And for us in the team, they wanted, in Terroir, they wanted to find a story of how could we add, how could we keep the building as it currently is, so we're not changing the groundscape dramatically, but add to the next generation, the next story of the building. And of course, with the precedent set by St. Luke's Health, it was decided that they were going to go with a mass timber structure and look to incorporate as many of the existing features on the ground floor as possible in the final design. Here you see some of the competition imagery where they would have the timber structure going right from the ground floor in a perfect situation and complementing around by keeping the heritage trusses and the facade. The adaptive reuse of the existing brick floor facade and the timber structure was quite important in terms of our offsets in the calculation of upfront carbon, which also greatly impacted some of our calculations when we were looking at both Green Star and net zero calculation methodologies, which I'll talk about in a little bit. And as mentioned, the biggest aspect for them is not wanting to change the whole ground floor plane, wanting to keep it as traditional as possible and add to the next chapter of the area. Here's one of the models they created as part of the competition. Also some imagery of how it would be complemented around from different perspectives surrounding the building, just to show it could be a beacon of a building, a new chapter for the city of Launceston of how we could look to develop more sustainable and biophilic buildings in the future. Here is some key points around this. So the traditional facade had to be maintained. As discussed, it wasn't a formal heritage requirement, but certainly had other benefits in terms of cost, carbon reduction, and the like. The building itself is 8 stories high, just under 25 meters. So we avoid all of those great topics around air pressurization and other additional requirements. Level 1 and 2 ended up in the final design being concrete post-tension structure for 2 purposes. Number one, in the ground floor plane going up to the first floor, we have an open staircase. So we had to make sure we had fire compartmentation. The only way to do that was to keep we had a 2-hour fire requirement there, so we had to make it a concrete structure. Also, this building was in a high floodplain, so we had to find and make sure we were using the most robust materials possible to design for that. Levels 3 to 7 were mass timber. Level 6, which you see there, which is the balcony level, that's actually a timber concrete composite slab, so we have much higher loadings on that structure because of the pot plants and other formal things out there, as well as we wanted to be because it's exposed to the weather, we wanted to be able to feel more comfortable with more traditional ways of waterproofing these sort of exposed areas. So again, we added elements like Zypex into the concrete admixture, which helps with water tightness. And then we could waterproof on top of the concrete using more traditional poly-based roll-on applications. The timber cladding on the roof. So when we looked at the roof structure, there was a couple complications there we had to consider. It was double height, those external columns, so quite tall in nature. Because it was going to be open to the elements, we had to consider the durability of the timber used. We had to make sure that it was a durability 1 or durability 2 class timber to make sure it would last, again, the 50-year plus design life required for this building. When we started evaluating what species were available, we started thinking about, okay, is this cost competitive? Can we get it in budget? And the realization that we had is if we were to look at sort of a durability class 1 or 2 timber, naturally in Australia, it would fall towards a super hardwood out of North Queensland, looking at meerbow, spotted gum, potentially Akoya, because it is a chemically treated timber, even though it is radiata pine to start with. It goes through a chemical vinegar treatment to bring up its durability. But all of these timbers had either fabrication complications. We couldn't get them in the sizes we needed to support the loads and the height, or it comes at a cost complication. A lot of these timbers were in excess of 15,000 a cubic meter, which didn't fall within the project budgets. So we actually ended up going with a steel frame roof system, and then cladded using this durability. We ended up with spotted gum, actually, timber being cladded. Again, trying to use right products in the right situation. Some of the project highlights. So the base build of the structure took less than 50% of the time to complete than a normal concrete structure. This had significant benefits on site, of course, reduction in prelim costs, especially going in through a Tasmanian winter. We wanted to make sure it was up as efficient and quick as possible. The CLT actually came from 2 completely separate manufacturers in Australia. The majority of the project came from XLAM, which were level 3 to 6, and the top level, level 7, came from CASP, a very small manufacturer in the northwest of Tasmania that makes CLT using eucalyptus nitens hardwood. We had worked with them previously, helping to develop their products as a different project, but this was the first big commercial building that they're able to contribute to in Australia, providing CLT. Both was fantastic. And then the glulam, we wanted to, as part of the project, use as much local as possible, but unfortunately, because of some procurement topics, we had to go to Europe to get the spruce glulam. So that was imported all the way from Germany from company Hess. Again, another brilliant manufacturer doing a lot of projects locally, and they were great to work with. All 3 were great to work with on this project. 100% of the operational energy used is offset by combination of either solar panels on the roof or by local renewable energy sources. In Tasmania, they're quite popular for hydroelectric. And so this building is either powered by the solar panels or the hydroelectric facility just down the road. And in terms of building physics, we're able to achieve 25% better energy efficiency than code requirements. Again, trying to think of healthy lifestyles, think of the next generation of buildings. These were key components. For us, we looked at charting a way. So in the carbon map, we were thinking, okay, how could we optimize carbon? How could we get it to be as reduced as possible? While we didn't go for any formal recognition, we did use the calculation methods to chart our pathway. So we were running both the zero carbon certification, which I believe is part of the Living Futures Challenge, as well as the Green Star rated calculation method. By adapting the reuse of the existing building, the CLT structure, and the exposed surfaces, we're able to achieve either 28.8% reduction using the Green Star method or 59.3% using the zero carbon certification. For us, we wanted to see how far we could go while still maintaining cost competitiveness on the project. So we looked at everything from 10% of products with EDPs. We looked at carbon neutral products. We looked at reduced carbon concrete. We looked at carbon neutral concrete. We found that if we were to it using every option in the market, we could have reduced this project by 41.9% using the Green Star rating system, or the 76.5% using the zero carbon. But with Tasmania being in the location it is, and the Tasman Sea generally regarded as the most expensive transport location in the world, we found that we just were getting more and more expensive compared to maybe what we could have achieved if this was built in, say, a Sydney, a Brisbane, a Melbourne. So we settled on the where you see there in the current design, which is still quite a nice outcome for the project. The proposed building includes also exposed building services. This means that embodied carbon associated with the suspended ceilings typically used in a concrete frame building were removed as part of the upfront carbon calculation. Again, trying to expose as much of the timber as possible, leaving the building more of a warm shell and core, if you will. So the design process. For us, on this project, we undertook the timber structure engineering. This was undertook by my colleagues, Vincent Lestang and Dr. Flavio Vanaga, overseeing him. We assisted with the procurement strategy alongside the ECI contractor. We did the acoustic design on the building. We did the cost planning advice in collaboration with the local quantity surveyor. We did the construction planning in collaboration with Fair Brothers, the ECI contractor, who did really an amazing job on this project. We did the technical report for the Tasmanian Fire Brigade in collaboration with WSP, the local fire engineers. We did the technical report for the insurance company for St. Luke's Health, and we did the LOD 400 modeling on this project, independent of the manufacturers. That was one of the advantages that allowed us to really go independent to the market and be able to bring several different options for procurement. What we've seen in Australia in particular is that there's a lot of great designers in this country. A lot of projects we see are recommending that they get producers involved very early, even sometimes after schematic design phase. On some projects, we would absolutely agree this is certainly an advantage, especially if you have a formal mandates of local procurement. A lot of these local guys are so busy, they have long lead times. It's great to get them involved early. For projects like St. Luke's, where there was no real formal requirements, we really had to figure out a way to be as independent as possible to meet budgets, to meet timeframes, and make sure that the building obviously stacked up more than anything for feasibility, because there always was a risk that the building could get turned back into a concrete structure and business as usual. So we had to make sure that we're meeting what was set as the formal budgets, which were that comparative of a concrete structure. So for us, we took this building a little bit more in depth. When we did the initial feasibility studies, we were looking at all procurement options in the market. We were looking at CLT floors, glulam beams, LVL structures. We were looking at lightweight cassettes, and of course, hybrid options. We did cost studies and feasibility studies on all this. We ended up landing on the traditional CLT and glulam structure. But then it also, we had another layer of complexity. We had to think about procurement. Okay, there's so many different glulams in the market, especially, when you compare Australian hardwood options versus European spruce. CLT floors, we had to consider, okay, are these coming from Europe as well? Or are we going to push with local options? For us, we actually ran several different, through feasibility and schematic design, several different design options. Because when we're designing these buildings, we had to think from an architectural perspective, what was the floor to floor we had to achieve? If we were doing CLT out of XLAM, for example, who ended up supplying the building, that CLT had a thicker floor than, say, the spruce out of Europe did. And of course, when we were working out the floor to floors, we had to be planning for the worst case situation, not the best case situation. The same went for the glue lamp. The glue lamp ended up being spruce. If we would have had a local producer, this of course would have been more slender in nature and given us more generous floor to floors, but we would have cornered ourselves if we would have designed just for one product right from the very start. We would have been locked into one producer, one cost, which we weren't sure until design was 100% done, which could be a year away. So we had to keep our options open as long as possible. So for us, that was very important. We had to think about the service class design. We had to think about, okay, because we want to have as much not as much intervention. We wanted to be healthy building. So are we going to go with, say, mixed mode ventilation where we have natural airflow on the building? If we did, this could have an impact on the timber. This will change naturally the humidity in the building, and of course change the moisture content in the timber. Depending on how much moisture is in the timber depends on the strength grade. This wasn't so much a topic on this project, but certainly for projects that we've worked on in Sydney and Brisbane and other regions of Australia, this is absolutely a topic, more so where we're trying to get mixed mode ventilation and natural ventilation in on a project that's in a very humid environment. We have to think about how it'll affect the timber. So this was something we had to do a sanity check on to make sure that we're all designing in the same direction with the same thought process. Of course, naturally, timber, it is a combustible material, so we had to think of the fire requirements. First, we had to think of compartmentation, and we landed on this project on each floor having its own separate fire compartment. We were able to reduce the FRL from 120 to 90 minutes, but one of the ways we're able to do that is actually to do what's called a time equivalency calculation. So we worked with my colleague, Dr. Michael Klippel, out of Zurich, and he assisted us with the time equivalency calculations as well as the connection detailing on the project. And that basically means that he took each compartment and we ran some finite element models to say, right, in the event of a fire, how exactly long would a fire last? Would it actually get to 90 FRL? And so he ran thousands of different scenarios through the software, different iterations of how much facade you lose, how much fresh air is being introduced, how many kilojoules of energy are being produced in the event of a fire, considering we wanted to leave the soffits exposed. We looked at different adhesives in the timber. How would that affect different charring rates? And again, adding to the charring factors. And what we found in this instance, that actually in the event of a fire, the worst case situation was the fire would last 62 minutes. So we knew that a 90 FRL was more than safe, and that actually in the event of a fire, the building wouldn't collapse. It would eventually put itself out. We had to think, of course, on the timber systems being used. We had to think, the timber system's been tested to AS 1530.4, the glue lamp and the CLT. Did we have to encapsulate or could we leave it fully exposed? We're able to, flesh out these things during the time equivalency calculations. Species selection, again, different species have different charring rates because it's based on density. So we had to really consider this in our charring factors when we were doing the different situations on the floor to floor ratios in the initial sizing of the elements. And of course, we had to have a detailed fire engineering brief from the local fire engineer. Again, we worked with WSP on this project, who did a brilliant job. We had some great, robust conversations, and we're actually able to land on a design that worked really well, complemented timber while keeping it as a very safe design, and getting the Tasmanian Fire Brigade on board to ultimately sign off on the project. For us, the detailing is the key, and this is some of the initial details that we come up with here. For us, we needed to demonstrate, and this is what we went to the fire brigade with. We didn't go to them with, say, just general information. We actually went to them with concept details to show them how these are tests that we've done previously, either AS 1530.4 tests with different people or European tests. This is how it works based on the code. Here you see some images on the left of some testing that was done previously, and showing how the connection will always be protected, and that's why we're able to calculate charring factors. Here on the right-hand side, we're actually with the dotted red lines demonstrating exactly where we're expecting the charring factor to finish, and demonstrating the fact that the connections will always be protected We're also adding in, where the beams come from, what are the additional elements that need to be added, such as stone wool, or sometimes we did grout infilling on where we had bigger gaps than 2 or 3 millimeters to ensure that the fire couldn't get in and around and the temperature wouldn't affect some of the steel or aluminum connectors. These are very important in the detailing to make sure that everyone's on board, the authority is aware that technically it's well thought through, but also this is important for the builder to understand who's doing what's happening in factory, where different things are, what connectors are being put on in factory, what's being assembled on site, where to get it from. These are all very, very important for many facets. The acoustic design as well was very important for this building because it also played into the service reticulation strategy. And of course, from an architectural perspective, it played into the idea of floor to floor ratios. Here we ended up having a raised floor. So that allowed us to do some low-level reticulation of services, which gave a very flexible floor plate for future use. So we can go on from adjusting the internal fit out many times over with different tenants over the years. So we had floor-mounted GPOs. We also had data points in the floor system, and it was really only the major electrical runs and the mechanical and fire sprinklers and wet elements that were going through the beam penetrations. But again, this was important to consider very early in the design piece because it can affect the floor-to-floor ratios. And we wanted to make sure that we weren't designing ourselves into a corner where we had, height under beam of, less than 2.7. MEP service reticulation, I would say, is one of the biggest conversations because it can have the most impact. So for us, we worked with a brilliant MEP designer who ended up designing up to LOD 300 level. So we were all working in 3D on this project. This was able to give us absolute clarity in terms of penetrations, where they were, could we make them work in our beams? We overlaid our model of the timber structure on top of theirs. We're able to do real life coordination. This coordination was done in collaboration with the concrete engineer on this project, which is Gandy and Roberts. They had a brilliant BIM manager, Klaus, on the project who really helped us with the coordination, with identifying key risks and working out strategies of how we weren't overcompensating each other or there wasn't any clashes. This really gave the builder also big confidence in costing the project and bringing their subcontractors on board because we were actually able to give them, again, how many linear meters of pipe, how many linear meters of conduit, how many linear meters of mechanical duct were required. So again, much more cost certainty on this project than I would say traditionally done. And for us, it also was able to give us assurances as to where the penetrations were on the beam. So we could work out reinforcement. We could work out the fire safety strategy of how these penetrations were protected. And we could design it with absolute confidence. We actually ended up including, again, some extra holes and penetrations which are covered for future use. So those penetrations are there, but they're covered with the timber plank, just so that in the future, if they do require more services, because they end up, instead of one single floor tenancy, they end up going to, let's say, 2 or 3 per floor. This can provide more flexibility. Again, something we had to consider in the design. Architectural considerations. So, if the timber is exposed, is the architect satisfied with the visual quality of the timber species? So again, not only do you have to choose the species, but what do you want it to look like? Do you want it to be a little bit more rustic with more knots, or do you want it to be fully sanded so it looks more like a floorboard and smooth? I mean, all of this has cost implications and, of course, architectural considerations. What is the base cost per cubic meter of the timber species selected, and how does that equal your feasibility requirements? As I mentioned before, if you're looking at some of the super hardwoods here in Australia, they come at a super price tag, but rightfully so. I mean, they're very dense, they're slow growing timbers, they're very hard to work with from a manufacturing perspective because the density is almost 2.5 times that of a, say, spruce or radiata pine softwood. So of course it comes at a cost premium. But the other benefit is that in the external environment, it doesn't have to be, or some species don't have to be additionally treated. But you have to be aware of the species you're selecting and the costs associated with that species because it will affect your feasibility. If you choose a specific species, what are the procurement options? Again, you need to go into these sort of projects with eyes wide open, and that's why we left as many options on the table as possible until just starting detail design. And that's why it was so important to have the ECI contractor on board, because they're able to run a 2 or 3 stage tender on the project to get some real cost certainties, to weigh up the pros and cons, the risks associated with that. And at the end of the day, that's why we ended up with the producers that we have, because we're able to, I guess, have assurances that they're able to meet the cost expectations of the local market and the time frame required. But again, this can have an effect. And then we also have to consider, from an architectural perspective, what do you want the building to look like in 10, 20, 30 years? Does UV protection need to be considered for discoloration, or are you happy for it to age over time? Again, all of these have implications on the ongoing maintenance cost of a timber building, the visual effects of a timber building. I would say it doesn't have so much effect, especially if it's locked into a service class 1 internal environment inside of the structure. If it's kept out of the elements biologically, timber will last, in theory, forever. You see great examples of this around the world. But visually, of course, they will change over time. This is more of an architectural conversation. The benefits on site. So again, we had Fair Brothers on board, for just over 6 months, helping us to design this building. So what we had was a 50% quicker installation rate, which had great benefits in terms of reducing costs compared to concrete and prelim. There was no waste on site. So there was literally a team of 8 to 10 carpenters. This building was put together by Savcon, again, another brilliant specialist subcontractor to Fair Brothers, who put this together extremely quickly, and there was literally no waste generated on site. I believe they said that they went through about 1 skip through the whole structure, because all of the waste that was generated during the production process of the timber structure was kept at the manufacturers, and they use that to produce other products. So it went together very quick, very efficiently, and there was 1 or 2 deliveries per day, so there was no disruption on site. We did have a concrete core in this structure, but again, working with the local engineer, Gandhi and Roberts, they come up with a brilliant idea for a prefab, precast a core. So again, it was a prefabbed offsite. It was delivered on site in a prefab sense, and they were lifting it up as a box, stacking on top of each other. So following the same mantra as the timber, so that they weren't critical path. It was just another thing in the lifting sequence, and they were actually able to freestand that whole entire core even before timber started on site again, which was a great advantage. The lighter structure, so timber itself was 50% lighter than what we would have had with a fully concrete structure. So there was significant savings in the foundation loads and the core design, because there weren't as much lateral forces or weight of lateral forces. The timber was left exposed. So when we were doing the cost planning, one of the biggest things was that when you compare timber to concrete, yeah, absolutely. There's no argument. Timber is definitely more expensive than concrete. That's never been an argument. But always the argument is you have to think the peripheral elements, and you need to be really considering the cost planning from a cost plan 3 basis. As I mentioned, this was put together at 8 to 10 carpenters, not 40, 50, 60 people on site with an FRP package. So there's a significant reduction there of prelims. Same with building 50% quicker. What are the prelim costs per week? And you can reduce that by 50% in the structure in this case. The lighter structure, foundation loads were less. Where's the cost reduction compared to that? Wellness, in this instance, we were able to make it fire safe, so we could leave it fully exposed internally. So we need because the timber's exposed, it replaces the gypsum board, the paint budget. All of this needs to be considered as well as in the cost analysis. And easy construction. It's a lightweight material. So we were using a much smaller crane than what would have been needed to lift post-tension strands all the way up and at radius. So that also need to be considered as part of the analysis. For us, this is something that we did as well. When we started the LOD 400 modeling, we worked with Fair Brothers to figure out exactly, okay, how are we going to build this thing? Where are you going to put the crane? What's the order and sequence we want to start with? And so this was what we did in our planning stages as we worked out the procurement, and then we started the LOD 400 modeling. We actually worked with them and did some real life timing and modeling, so we could figure out the costs of putting this thing together from a time perspective. Also, this helped us to number all the individual elements on the project, which fed into the production sequence, the shipping sequence, and of course, ultimately how it was erected on site. We really babysat this project to make sure that everything got done as efficient as possible and that we're all working on the same page. You can get this benefit, of course, by a traditional, going out to 4 tenderers, but it just means that this happens later in the piece. But it does need to happen with a timber building, which is much different than, say, a traditional building. Generally, the builder doesn't really care where you start because it all has to be done. For us, we have to manufacture this somewhere else and then deliver it to site. So these sort of studies are imperative to understand the complications, the connection details, how the builder wants to put it together could determine, some difference in connection details and efficiencies. We want to make sure we're choosing the right products in the right situation. As I mentioned before, durability. Different parts of Australia have different requirements. And for us, we had to think about, as I mentioned, this is on a floodplain site. So while termites and insects on this project wasn't so much a concern, we had to think about fungus attacks, mold growth. We had to think about contact potentially with water. We did, long-term use internally and external environment. All of these were considered as part of the design process. Again, not all of them are relevant to this project, but certainly it was something that we had to tick the box to make sure yes or no. And if it was a yes, how are we going to overcome it? Hence why the top structure ended up being a steel frame cladded in timber because of the external environment, the long-term risk around having to get out there and having to maintain it as a pure timber structure. Whereas if it's a cladding, it's less of an importance. And then DFMA, as I mentioned before, one of the key reasons why we're able to get 2 different CLT suppliers from Australia on this project and the glulam all the way from Germany was because we did the LOD 400 model independent. So everyone worked from our model. We're able to, as you saw before, do the studies of the order and sequence. So we're able to then figure out exactly the direction of the haplaf joints, what connections were done by whom, the penetrations, all of that was modeled by us. And then basically it went out like a kit of parts where that was made in Germany, this was made in Albury-Wodonga, this was made in northwest Tasmania, all coming together to 1/10 of a millimeter tolerance on site for a great outcome on the project. It gave the builder ultimate flexibility of procurement. They were more procuring like a shopping list, not necessarily locked into different producers so early in the piece. This was only the last few weeks where they did the final tenders that we were able to get the final quotes and pick the final selection of producers. So we stayed as independent for as long as possible. And then, of course, fabrication. Most of you, I don't need to tell you how these things are made, but just some visual imagery of what it's like to make these timber elements and why it's so important to be working in 3D, because literally these elements are being made by robots, CNC machines globally, either locally in Australia or elsewhere. So we really had to think about this in depth and think of it from a more 360 point of view, because we couldn't leave things to a DNC on site. We had to figure out penetrations early. We had to think about procurement strategy. We had to think about fire. We had to think about constructability, because we had one chance to get it right. If it comes on site and a panel doesn't fit, we can't just order one and it's there in a couple hours. We're talking weeks and months. So it's so important to have the right people around the table to determine all of these things early. I almost say it's kind of reverse what I found here in Australia, where a lot of people do a base design and then everything's DNC to a builder. It almost needs to be reverse. I still feel that, yes, the builder needs to have some DNC responsibilities, but in terms of the timber structure and the elements that influence the timber structure, and primarily the MEP services and acoustic design and fire design, this has to be done well in advance, and this has to be picked up right from concept moving forward. So again, just to reinforce, early engagement with timber design team is key when designing a timber building. It is a different design process and more considerations need to be done earlier than later. Project setup needs to be made early in the design process to avoid abortive and costly work. Timber building considerations are greater than just a traditional architect and engineering role. Choose the right timber product and species. It's imperative to achieve optimal cost solutions. I mean, as I mentioned, this project ended up being CLT and glulam, but at the same time, we could have easily done lightweight cassettes, timber cassettes. The only difference would have been that we would have had to fire rate them. We couldn't have left it exposed. We would have had to have put 2 layers of fire check underneath. So again, different species, different products have different advantages, but also disadvantages. And this needs to be weighed up depending on what your drivers are and cost tightness of cost is. The external and internal environment, procurement strategy, FRL calcs, and connection concepts have a huge role to play in the species and product selection, and these need to be considered early. So you're building the building blocks like a Lego. Consideration of potential suppliers, specific chosen species is required, and thorough understanding of the benefits and their associated costings is imperative to complete a cost analysis. Thank you.
Beautiful. Thank you so much. Yeah, thank you. Thank you so much. It's not every day that someone comes on these webinar series who can just run the victory lap. Like this really that was extremely obvious that that yourself and your team have A, done this before, and B, really ran everything into the ground. So thank you for coming and sharing it today. I'm sure everyone got a massive amount of value out of your presentation. We've got a few questions that come on the chat through your presentation. The first one was a comment saying, "Oh no, what's happened to my favorite Launceston cafe?" But I'll ignore that one.
It's still there. It's one block over. I visited it when I did a site inspection, so don't worry. It's still there. The coffee and donuts are just as great. Yeah.
Phew. Okay, so the first question comes from Lewis Wallace. Did the selection of GLT from overseas also help with fire demonstration and research to show how the charring occurred?
Well, I wouldn't necessarily say that was a driver because we could have done it easily, very easily out of great local products as well. The only thing that would have changed would have been the density calculation. The denser the timber, the slower the burn rate. So yes, of course, in Europe, there's much more tests. And yes, there's more decades of experience and more experience using spruce as glulam. But we could have very easily have done it. It just would have been a different calculation and there would have been a different thickness of charring and zero strength layer required.
Right. So it definitely wasn't a case of there not being enough data to make a decision.
No, absolutely not. No.
Cool. The fire modeling was particularly interesting for me and also in the crowd as well. A question here from Stuart. Did the fire modeling consider the loss of compressive strength of the residual timber for the elevated temperature behind the charring?
Yeah, exactly. So we followed in this instance the new Eurocode that's out there. So we've actually did the normal charring element, and actually for the CLT we had to do the step charring element because we didn't use a high performance adhesive on this project, and also we had to include an increased zero strength layer. So I believe in the calculations our zero strength layer was about 15 millimeters. In the old code, I think it's about 7. So we increased that based on new research and new recommendations to again demonstrate that we were thinking about it more robust and more conservatively.
Thank you. Jackie Bates asks, for durability, did you end up specifying treated timber?
No, treated timber wasn't required on this project because it's locked in an internal environment, service class 1. So we didn't need to treat it for any specific reason internally. And then that was part of the driver why we ended up going with a steel frame for the double height columns in the roof structure. They are cladded in spotted gum, which again is a higher durability, but we still would have a maintenance requirement on that. And we found that to do it in a solid element, it was a very high risk long-term to get out there and maintain this structure and to put coatings on it, and our safety and design, it just wasn't a risk that was overly acceptable, and the cost associated with not only the timber itself, but also the long-term maintenance. And that's why we ended up with a steel frame structure cladded in the timber so that it has less of an importance and less of a formal requirement to be treated. It's not formally treated in terms of H3 or chemical treatment, but they are lacquering it for more UV stabilization more than anything.
Thank you. Yeah, and that point on the steel I think is fantastic because people can do backflips and tie themselves in knots trying to get a level of authenticity that perhaps doesn't actually meet the performance requirements that are needed. And it's nice that whenever we do get into trouble, steel is always there to save the day, being like the perfect engineering material.
Well, I wouldn't go that far, but certainly it's this project to me is quite special because I think it's a great demonstration of the buildings of the future. And I think this is where a lot of us get caught in our own world where we think if it's not 100% timber, it's not a timber building. What we're seeing out of Europe, in particular the UK, which has been great at it, and what I think needs to be adapted more here is if we want hybrid timber buildings to be more,
Sorry,
they could, no problem. They could be just as cost competitive, but we have to use the right products in the right situation for the right outcome. So to think that timber ticks all the boxes all the time is just unrealistic. I think us as designers have to be completely open to the right materials and the right situation and how that impacts the architecture and the engineering. So this building's fantastic because it has a little bit of everything, but the main focus more than anything is the timber structure, but it really ends up being probably about 60% of the whole equation, not 100%.
Yeah, and I think if I was to put your whole presentation into a word, it'd be balance. It'd be about that balance, which I suppose is what all engineering is. I want a question here from Travis. Interesting that there seemingly was two fire engineers, WSP locally and ETH Zurich, obviously more in a research space. Can you explain any more about the reason for that and the separation and collaboration between those two roles?
Yeah, absolutely. So it wasn't with ETH, even though Dr. Klippel is a research fellow there. He actually owns a company called Ignis Consulting, and they're shareholders of Timber Design Studio, who I was an owner with as well. So him and I have worked together for many years. And what the difference was WSP was in charge of the more holistic approach of the building, travel distances, FRLs, formal sign off here. And where Mikael was, arguably the best in the world at is actually figuring out the connection details. We're designing it from an engineering point of view, so we're figuring out the chars, things like this. But when you look at it, is the steel or aluminium shear connector, for example, on a post and meet connection, is that safe? And so he comes in and analyzes that either through thermal modeling or through past experience of those tests and says, actually, it's not. We need to add, rock wool around here. This gap is too big. That construction tolerance, when we had a glulam beam coming into precast concrete, we had to allow a much bigger gap there. Okay, how are we treating that gap? This is where those advices are just amazing and helps us to, not just think about it from a structural point of view, but an aesthetic and a fire safe point of view. So for that, it's always important not just to have a holistic fire approach, but someone who can get into the micro detail and make sure that we're getting the building authority sign off. And I think that's so important to come to these, to the fire engineers and to the local fire brigades with more of a problem and a solution rather than a problem and sort of holistic idea of how we might do things.
I bet that makes the conversations a lot easier for you to push through and educate and bring them along the ride. How are the local fire authorities to the new approach?
Well, they were, Tasmania is a little bit more relaxed at the best of times, but they were brilliant. Other projects we've had in other states are much more complex. And again, if you're coming prepared to have a real technical conversation, we found them to be very forward thinking and very willing to listen and willing to find compromise. The couple projects earlier we were involved in where we were brought in late in the piece to provide some of this technical engineering, we found that some of the solutions or the proposals were just way too generic and they wanted more of the detail. So I think the more you come to these prepared to discuss the detail and knowing what their key critical things are, just really proving that people can get out safe and the buildings aren't going to collapse. I think those are super important to bring to a conversation.
Definitely. I find it remarkable that you effectively demonstrated burnout well below the FRL requirement. That's remarkable.
Yeah, it's something, again, what Mikael and his team at Ignis do so brilliantly, but for us, we do it on the majority of our projects because it's not, with the Australian 30, 60, 90, 120, that's great in theory, But with timber, people still see it as a high risk. So we have to go the
Mm.
next layer to say, well, is 90 actually efficient? And that's one of the reasons why people can have confidence going from 120 to 90, because we can prove through calculation methodology or advanced modeling that that is actually right. It's not just a guess because of X, Y, Z. It's actually, it can formally be done. And these are the reasons. We do it more so in Europe. The UK it's almost mandatory after Grenfell for these sort of calculation
Yeah.
basis. Mikhail's done some great projects with the London Fire Brigade there, which are, if there's conservative, they're the complete, they're the extreme of conservatism because of Grenfell. So for us, this is mandatory, and he's certainly one of the world leaders, and we use him on the majority of our projects where this is a sensitive topic.
And have they developed that set of standards? So obviously, whenever you talk about FEA, there's always the black box problem, and you have to interrogate what's going on. Did that standard of assessment develop a lot recently as a result of Grenfell in the UK?
Yeah, I would say it's always been in the research of Europe for the last sort of decade as a primary focus, knowing that as people want to go bigger and bigger, and that is always going to be the sort of holding force. So,
Mm.
other great firms like Rise out of Sweden, ETH Zurich, Edinburgh, these firms and research universities have been brilliant at going that next level. And now it's becoming more into practice as it becomes more the forefront. It's more of a formal requirement. So.
No, excellent. It's a really good sign of what's to come. And there could be a day when we rely on the burnout capabilities entirely, which is more an accurate way to go. What are your thoughts? So you on the tendering and assembly, Savcom's involved, and they're a brilliant, highly reputable assembler who obviously know their stuff. This comment comes from Peter. I'm sure Savcom would agree that a specialist contractor involvement through the design phase is key. What are your thoughts on that from an assembly point of view?
Absolutely. And I would say I put forward 3 or 4 options for them to consider. They ended up choosing Savcon. But for me, more than anything, it was so imperative when we were doing the LOD funded modeling, like I showed there, where we did the sequence in order. We had to make sure that whoever wasn't it was putting together wasn't inheriting a dog's breakfast. So I say the ECI contractor Savcon was part of those conversations, but more than anything, it really helped to alleviate a lot of contingencies that the builder had early. This
Yeah.
was the first major timber building. Having Savcon on board to take the risk, to provide the guidance, to provide assurances. It was a massive reduction in what they anticipated from a prelims point of view, a program point of view, and subsequently a cost point of view, which helped get the project. I didn't really talk about it, but our budget was X amount. We found that the initial cost plan was much, much higher at the risk of going back to concrete. But St. Luke's were brilliant in wanting to keep to their strategy and vision of a healthy building. And through this organic bringing in of the specialist, Savcom being one of them, we were able to bring down the cost to just slightly below what the budget was because of these alleviations of just fear of the unknowns.
Mm. Oh, well, excellent. You guys are obviously stellar at ferreting out the unknowns and bringing them to the surface. That's a good question. At what stage did the builder start to be involved?
I would say right after schematic design. So it went out for expression of interest. They went down to the final 2. Fair Brothers ended up winning that expression of interest, but yeah, they were basically, once we started schematic design, finished schematic design, they were brought on board. And in our schematic design, we had a couple options for each, like I mentioned. We had a couple glulam options, a couple CLT options. One of their first tasks were coming on board is, okay, let's go to the market as a prelim tender, and let's figure out who's who in the zoo, what are the risks associated with each potential procurement option of the timber, time frame, cost, et cetera, how much work do they have, knowing that the building is going to need to be produced in this time window. And that's where we ended up, before we started detail design, ended up whittling it down to what we have now, the 3 there. Now the glulam was kept very late because with spruce, I think they ended up going to 6 or 7 tenders the very last, because that is much more independent, because in Europe it's all the same, some slight variations. Like I said, Hess ended up winning it, but for XLAM and CAS, we knew from right from detail design, okay, it's going radiata pine for these floors, and that floor, we know the indicative prices within a range, so we know it fits within the budget expectations, and the glue lamp could be left impartial and then formally tendered at the end of detail
Mm.
design, which is what we did.
What was the main reason? Like, are there any key reasons that put Australian suppliers out of the race for the GLT supply?
I think at the time it was just purely workload. I think
Gotcha.
there was, we went to several producers. A couple of them, it was cost much more expensive than going the European option, and then for the other one, a fantastic option. They were our first choice, and I think it literally come down to how much workload they had on at the moment. They were doing a couple other major projects, and it was a bit further along in terms of procurement. To be able to get their product on. So we ended up having to go to spruce only for that reason.
Well, it's excellent that there is a wide variety of suppliers there to that. I'm guessing it was the same for the Cusp XLAM split. It was because Cusp just had a supply limit, being a smaller supplier. Is that correct?
Yeah, exactly right. I mean, that's exactly where we ended up. Initially, the idea was Cusp potentially could do everything, but again, further exploration. It's a really small factory. They do a very niche and bespoke product. It's the first ever hardwood CLT, so it's it is slightly more expensive because it is a premium product. I mean, if you ever get a chance to visit it, it's like a joinery piece up there. It's not necessarily a rough and ready CLT panel. But again, we had to keep our options open. And so XLAM was fantastic because they did, like I say, 90% of the building and the top 10%, which was actually St. Luke's new headquarters in Launceston, their own office. They decided to go with Cusp as a more bespoke piece. But yeah, it ended up working out quite well for everyone.
Oh, it's beautiful that there is an option to go with bespoke CLT, the nice joinery quality, and it calls into question the difference between joinery quality and structural quality. So it's important to
Yeah,
keep.
and I mean, I say that, but I mean, again, I don't mind the Xlam product. It's
Mm.
fantastic. It looks great. The building looks fantastic. It's just that with the hardwood, it's a whole different dimension, Yeah.
I've got a question here from Anna. Was the CFC sheet in the floor system adopted for fire or acoustic performance? Both.
Uh, no, actually, there was no CFC, so that's an old element. So basically, what we had was in the floor system, we have the raised floor, and it's on rubber gaskets, and then it's about a 150 raised thing. The CFC sheet was what we come up with originally, but what we found working with the engineers is actually we can get rid of it, and because we got charring factor to work from both directions. So we didn't need to actually have it for a formal fire requirement in the end. So we were able to get rid of it for cost savings and just keep with the only change was that we had to put the raised floor on rubber mounted elements for
Gaskets
discontinuous,
for
yeah,
the
gaskets. Yeah,
yeah.
thank you for discontinuous construction.
Yeah, no, beautiful. Thank you. All right, let's do one last question. Was earthquake wind analysis and design carried out by BG&E or the concrete engineer or both?
It was actually carried out by both. We were given the forces of expectation, both earthquake and Lynn, from the local Gandy and Roberts. So they gave us the local requirements. And then we did the analysis based on that in our modeling using Drupal. So for us, we actually found that we don't need the cross bracing whatsoever for lateral stability. So
Wow.
actually, this is another topic. We were brought in after the competition and after sort of the competition was won. So the competition, it's a beautiful building. Naturally, they assumed you'll need cross bracing for stability purposes. Through our analysis, it ended up that actually we don't. The core is big enough, central enough that it provides the stability itself, and we're able to get the connections to work in the forces. So they're held in by a few screws for aesthetic purposes. There is no,
Really?
there's no formal requirement for them laterally, but we did the
I love that.
overall fire. We did the overall lateral analysis, and then we come back to Gandy and Roberts and said, right, these are the forces that we're getting at your core, and then we designed that connection and collaboration together, so that, of course, both were supporting each other.
Oh, beautiful. Well, what a story. And thank you for answering all those questions. We got some fantastic responses from the audience. Yeah, I can't thank you enough, Dane. Thank you for being here. The audience definitely loved it. Thank you. I'll do my closing spiel now and talking about the upcoming events. But yeah, thank you so much again for coming here. Really appreciate it.
No, thank you for the honor.
All right, so I'm going to wrap this up. Let's go to, yeah, here we go. Okay. So yeah, thank you all for coming, and thank you again, Dane, for being here. It was a spectacular presentation. I'll now tell you about the upcoming events with WoodSolutions. So there is an upcoming event in Sydney, the Sydney seminar on Thursday, the 22nd of February, 8:30. It's just a morning seminar. It's covering passive house design in Australia, but also we have a very special international guest talking about active moisture management and moisture control in timber buildings. So that one's a really, really cool event, definitely worth attending. If you're in Sydney, please do check it out on Eventbrite. It's definitely worth your time. It's going to be a great morning, so make sure you get along to that if you're in Sydney. And of course, as always, make sure to get excited for the Timber Design Awards in 2024. We're going to set up for another spectacular round. And soon we'll be joined on the webinar series by ARM Architects, who are the winners of last year's competition with their refurbishment of the Sydney Opera House, which you're seeing right here. And next month's webinar will take place on the 5th of March at 11 a.m. And it's going to be all about Bulla Carthagin, the Murdoch University building, and a case study of that spectacular, massive, and well-versed building in many ways as well. So thank you so much for coming. Thank you, Dane, for being here. Tell your friends about it. Get onto the seminar, get onto the webinar for next month, and I'll see you in the next webinar. Thank you so much. Ciao.